Hello everyone, we are continuing crystal field theory. This is part 2. Please watch part 1 before passing on to part 2 so that you can understand it thoroughly well. In this video, first we will see the salient points of crystal field theory. Then pass on to its explanation. But before we continue, please watch the video completely. And if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. I am Anandavali from Guidance Education channel. I welcome you all to this new video from Guidance Education channel. Now we will see the details. According to the crystal field theory, metal ligand bond is ionic in nature and not covalent. Covalent bonds you have already learned. They are formed by sharing of electrons, whereas ionic bonds, as you know, is formed by transfer of electrons. Ionic compounds in general are crystalline in nature. Hence the term crystal. The central metal atom is essentially cation because metals have a tendency to lose electrons. So automatically this metal ion will develop an electric field. Hence the term field. I hope you understand the name crystal field theory. Second point, ligands are considered as point negative charges, and ligands can be either anions or they may be neutral polar molecules like water, ammonia, etc. For anions bear a negative charge, and for polar molecules, one end of the molecule will be negative and the other end will be positive. If the ligand is an anion, a negative charge is approaching the central cation. If it is a neutral polar molecule functioning as a ligand, then the negative end of the polar molecule approaches the cation. In either case, it is the negative field that approach the cation during bond formation. The cation in the case of the coordination compound belongs to the transition group, that is D block elements. The approaching ligand distorts the energy of the D subshell, which is a balanced shell. We will see the details shortly. We will complete the salient points. Thirdly, the effect of the approaching ligands on the energy of the d orbital of the central atom depends on the electric field of the former. That is, the electric field of the ligand. Different anions and polar molecules will have different electric field. That is, the strength and other features of these ligands will be different. So that will decide the effect of the ligand on the energy of the d orbital of the central metal atom. And this difference accounts for the difference in the shape of coordination complexes or coordination molecules. For example, the coordination complexes may be octahedral, square planar, or tetrahedral in shape. These three shapes are discussed in your textbook, so I mentioned these three. That's all. We said ligands are considered as point negative charges. The strength of this negative charge is not same. So the electric field offered by them also will be different. The arrangement of the ligands in the increasing order of the strength of their charge or electric field is called spectrochemical series. We will learn that after we understand splitting of the crystal field. Splitting of the crystal field is different for octahedral, square planar and tetrahedral molecules. First we will take up octahedral molecules. That is how the d orbital of the central metal atom splits when ligands approach it. In the octahedral molecule, there is one central metal atom which I have shown in orange color and 6 ligands in white color attached to it. Again, I use the letter M for metal and L for the ligand. This picture is in 2 dimension. In 3 dimension, it has octahedral shape. You have to understand that. Please note the metal ligand bonds. 2 are solid wedges and 2 are dashed wedges. The remaining 2 are straight lines. In chemistry, solid wedges are used to represent bonds which project outside the plane of paper, that is, project towards us, and dashed wedges are used to represent bonds which project into the paper, that is, away from us, and the 2 straight lines represent bonds which are on the plane of paper. That will give us more or less a 3-dimensional view of the molecule. How are these bonds related to the 3 coordinates x, y and z? I will note the corresponding alphabets z, x and y to denote the direction. When we apply this diagram to the first diagram, this is the y-axis and this one is the x-axis and the other one is along the z-axis. So from the diagram it is very clear that for the bonds along the x-axis and y-axis, one bond is projecting outside the paper, that is towards us, and the other one is projecting into the paper. Whereas for z-axis, the 2 lobes are on the plane of paper. Now we will proceed to understand about the energy of the 5 d orbitals of the central metal atom in the free state and also when it is approached by ligand, that is, when it is about to bond with ligand. In the free state, the electric field around the metal atom is spherical. That is, the 5 d orbitals have the same energy in all the directions. That is, all the 5 d orbitals are degenerate. It is customary to represent them as 5 boxes. Since their energy is the same, they are at the same level. We have already seen that these 5 orbitals are named as dx square minus y square, dz square, dxy, dxz, then dyz. Dx square minus y square and dz square are axial, that is along the axis, and the other 3 are in between the axes. What I have shown here is the metal bonded to the ligands in the octahedral complex. This is a different thing. Now we will see what happens to these degenerate 5 or d orbitals when it is approached by a ligand. That is, a negative electric field is approaching the central metal atom. For easiness of discussion, we will represent these 5 degenerate orbitals as 5 lines. These 5 degenerate orbitals are at a lower energy level in the free state, that is, when it is not approached by a ligand. When the central metal atom is approached by a ligand, its energy increases. This is because when the ligands approach the central metal atom, a sort of a repulsion develops between the electrons of the metal atom and also the negative field offered by the ligands. Now the energy of the d orbitals increases. So the set of 5 orbitals is shown at a higher level, denoting that its energy has gone up. But these 5 orbitals will now have different energies. Their energy is not the same. The degeneracy is lost. The average energy of these 5 orbitals is taken as 0. It is not really 0, but it is considered as 0. And that point is called barycenter. In the case of octahedral complexes, the degenerate orbitals which has gained energy now splits into two sets. This splitting is called splitting of d orbitals in octahedral crystal field. One of the set consists of the two orbitals dx square minus y square and dz square, which are along the axis. They possess higher energy. The second set consists of the remaining three dxy, dxz and dyz orbitals, which are in between the axes. They have less energy. They are energetically at a lower level. This separation of energy among the two sets of orbitals is called crystal field splitting energy, denoted by the symbol delta O, O for octahedral. For different shapes, the splitting energy will be different. The two orbitals with greater energy are called Eg orbitals, and the orbitals with lower energy are called T2G orbitals. The terms Eg and T2G are spectroscopic terms. Let me note the term barycenter here. The two Eg orbitals are along the axial line. So, when the ligands approach the central metal atom along the axial position, the repulsion is very great. Therefore, its energy increases. The T2G orbitals, which are in between the axial position, offer less resistance. Therefore, their energy is comparatively less. These orbitals are said to be threefold degenerate, and the Eg orbitals are said to be twofold degenerate. The splitting of the energy of the 5d orbitals when the ligand approaches it, that is the central atom, is called crystal field splitting, and the energy separation is called crystal field splitting energy. This energy will be different for different shapes of the coordination entity. The electric field of the ligand, we said that it is different for different ligands. That will decide the nature of the splitting. For octahedral complexes, this is the pattern of splitting. Among the octahedral complexes also, the crystal field splitting energy, delta O, will be different because the ligands will be different. In the picture showing the ligand metal bonding, which I have given there are 6 groups. But so far we were talking about 5 bonds. That is 5 orbitals. Please understand, we are discussing how the 5d orbitals of the central metal atom is linked to the ligands. Forget about the 6th bond, because the crystal field theory refers only to how the d orbitals bond with the ligand. I hope it is clear. We say the energy of the Eg orbitals increase by 3/5 and that of the T2G decrease by 2/5. We will discuss the rest of this topic in the next video. If you think the video was useful, do not forget to subscribe my channel. Thank you very much. Bye for the present.